Hey, my name is Yash, and this is my Physics 2211 Lab 5 presentation of motion of a falling slinky. So, the point of this lab is to model the motion of the falling slinky from static equilibrium as seen in the video I will show eventually. And the question we're trying to answer here is, does the bottom of the model slinky stay stationary just like in the video? So, the physics principles in this lab involve the position update formula, which states that position final equals position initial plus velocity average times time. The velocity update formula, which is that velocity final equals velocity initial plus net force over mass, which is acceleration times time. And then we have our forces. So Newton's second law of the momentum principle. So F equals ma, or F net delta T equals momentum final minus momentum initial. And the forces involved in the system are the force of gravity, the force of tension, and the drag force. So however, the force of tension and the drag force are going to be involved in two separate components here, as you'll see. So we were given this video on tracker, and basically we had to analyze it on tracker. And the origin was located at the bottom of the slinky, and the center of mass was always at the bottom, with the system being the slinky and the surroundings being the Earth. So here you can see the tracker data. So adjusted my coordinate axes to where x equals 0 for at the center of mass, and basically I had the 0 point where the bottom of the slinky was initially, while before it even got dropped. So that's why you can see the y position being constant 0 because the bottom of the slinky remained motionless. So next we're asked to code up some stuff on GlowScript. So the initial conditions, the mass of the slinky is 0.25 kg on line 35. All forces act in the j hat direction, so j hat is defined on line 51, and the drag constant in this case on line 54 is 2.6. So here we have part one of the calculation loop. So this involves the part of the slinky, the part of the video where the slinky is being dropped. So the only forces acting is the force of gravity and the tension force. And the bottom of the slinky remains stationary as it's trying to retract. So this is part two of the calculation loop. So basically the bottom of the slinky is now moving, so our center of mass is moving. And so now the forces acting upon it are gravity and drag from the Earth. And here you can see our forces, our velocity update formula, and our position update formula. And here are the results of our GlowScript code. So now for some analysis and discussion. So here you can see in the orange is the predicted model from GlowScript, and the blue is the observed model made by Tracker. The graphs are similar in terms of their shape. They both have a slope of 0 for a short bit of time, and then they have a slope of approximately y equals negative x. But you can see with the blue one, there's definitely some human error as there are discontinuities in the graph. So what if? So what if the slinky was thrown down instead of dropped in free fall? Well, it basically means the slinky would retract quicker. It, it wouldn't change anything about the motion besides the amount of time it took. And now for the actual question we were trying to answer in the beginning. Does the bottom of the slinky stay still? Yes. While a spring is retracting, the force tension is the same magnitude as gravity, with both acting in opposite directions. So F net in this case is 0. Because that's the case, the bottom of the slinky is in static equilibrium. But however, once the center of mass changes, then F net doesn't equal 0, and the slinky drops as a result. And you can see a change in the y position. That's the end of the video. Thank you for watching.